Hey, my name is Joe Morrison, and today I'm going to be talking about accuracy metrics for machine learning models and some of the common ways which they can be misleading if you don't understand what you're looking at. So, I work at a company called Xavier, and a lot of our work focuses at the intersection of machine learning applied to geospatial data, of which there's an increasing amount all the time. So more sensors are being deployed in space, in our cars, in our pockets than ever before, and that means there's more data to analyze than there ever has been before. So machine learning winds up being a really useful tool for trying to make sense of that data. Trick is that understanding how machine learning can be used responsibly and understood is still very much an open question for a lot of the folks that we work with and for ourselves. So while today I'm just going to be focusing on our work related to computer vision applied to Earth observation data, we see a lot of these same patterns across many industries, and machine learning is being applied to all kinds of data sets. So hopefully you can find some of the principles I go over here helpful, even if this isn't exactly in your wheelhouse. So I have a few goals for this talk. The first is to give you a better understanding of basic evaluation metrics that are commonly used for evaluating machine learning models, to give some examples of how they're applied in real life in our work, and also to plant the seed of, if in your job you're dealing with someone that wants to use machine learning or dealing with a vendor that claims to use machine learning to arrive at some valuable output, how to ask questions to figure out what they mean when they make accuracy claims, and kind of weed out the real useful partnerships from ones that are just going to waste your time. What I'm not trying to do today is get super deep in the weeds on statistical methods. I will cover some pretty complex statistical methods that are commonly used very briefly. If you want to go into more depth, I encourage you to follow up and do some of that research directly. I'm not trying to call anyone out for making up claims about accuracy or making irresponsible claims. I think this is a very difficult subject, and one that the industry is very much in the process of getting a handle on. And so a lot of people are very well-meaning, even if some of the claims that they make might be considered a little dubious. And I'm also not trying to say that I know the right way to do this or the best way to do this. This evolves on such a frequent basis. I feel like every 3 months to 6 months, I'm having to stop and relearn everything. So don't take it that way either. This is just sort of a snapshot in time, some of the, I would say, best practices that we've arrived at Xavier for dealing with machine learning. So quickly, before I dive into the weeds on how these models are evaluated, I want to just stop and address a more fundamental problem of what accuracy really even means, almost at a philosophical level. Because one of the patterns we've seen in our work is that no matter how simple the project is that you think you're working on, as soon as you actually try to automate the analysis of something, you realize it's much more complicated than you originally realized. Humans just have a ton of what you might call common sense, or resilience to new data that's never been seen before, that is very difficult to encode in a machine learning model. And so once you start measuring the accuracy of a model, you need something to compare it to. You need a gold standard to compare it to. And arriving at that gold standard can be very tricky. So for an example, we did a land use land cover project over Potsdam, city of Potsdam. And relatively simple land use land cover. We're pulling out things like buildings, trees, impervious surface. And what we found is that there are lots of edge cases that are maybe unintentional. So in this case, we've got overlapping categories. In this image, you can see there's a building, there's impervious surface, there is tree canopy, there are vehicles, which is a separate class, and there's probably some low vegetation actually towards the edge of that building that may be a little bit hard to see. And this is what the labelers chose to do. So you can see tree canopy, for some reason, supersedes both building and impervious surface and cars. So they labeled tree canopy when those things were overlapping. Why? Was tree camping more important? Maybe it just felt more intuitive. That wasn't necessarily a decision that was intentional, but it's a decision that affects how the model learns. So if you look at the actual model predictions, you see that it mirrors the choices that the training data showed it. So this is an example actually of bias. In this case, if you wanted to use this model to figure out where all the cars were, for instance, in a city, maybe you're trying to figure out vehicle utilization rate, trying to guess at how many vehicles just sit dormant on a lot all day. Well, you wouldn't catch these cars because they're parked under a tree, and therefore they're not counted in this model. And is that model wrong? Because according to the training data, if we compare it again, the model did really well. It adhered really closely to the judgment that it was taught. But in absolute terms, it missed those cars. It doesn't see those as cars. It hasn't learned that cars under tree canopy are cars. They're not cars to this model. So that's an interesting and very common use case. Another thing that you find is you have to make judgments about what data to feed the model. More data, more types of data, more diversity of data generally is a good thing, but not always. It can cause strange and unpredictable trade-offs. So in this case, we have cars parked on the roof of a parking garage. And when we trained the model using elevation data as an additional input, it got much better at things like identifying trees and building outlines. But suddenly cars parked on top of parking decks became invisible to it because it had never seen cars perched 20, 30 feet in the air. It thought if a car is 20 feet in the air, it's not a car, it's a building. So that's an interesting side effect of this new type of data, which had some benefits, some trade-offs. And the last thing, probably the most common thing, is that if you try to reduce the world into a few discrete variables, what you find very quickly is that it doesn't play nicely. So in this case, red is clutter, which is there's always sort of a garbage can class when you're doing land use, land cover, semantic segmentation projects. You can't reduce everything into discrete classes, and so you have to have some kind of catch-all. In this case, red, clutter. And you can see the annotators decided that this piece of construction equipment was a car, the dirt area was clutter, and this crane to the bottom right was clutter. Both are motorized vehicles you can drive around, but only one is a car. The model wasn't able to make that distinction. It saw almost all of it as clutter, and it saw some of it as low vegetation, which is clearly wrong. Some of it is building, which is clearly wrong. So it just got confused. And I don't blame it for being confused, because while I would feel that these two pieces of construction equipment are vehicles, another annotator might completely disagree with me, and I think we'd both have a claim to be accurate. Lastly, one of my favorite examples, here is an example of a food truck. And so you can see that it's a very long, extended truck with a sort of additional compartment built on the back, a kitchen built on the back. The labeler decided to call that a vehicle, which it is. The model ascribed building to the back half and vehicle to the front half. So it's a building vehicle, which in some ways may actually be a more accurate description of a food truck than just a vehicle. So you never know quite what you're going to get. The model is just trying to interpret the world as best it can given the vocabulary you've taught it. Here we see some data that's been distorted because of photogrammetry, and the labelers just decided those are all cars. That's not bad data. The model is able to also identify that those are cars. So that is one benefit of modern deep learning techniques, is that they can stand up to a fair bit of variety and even some errors in data without getting spooked. All right, so now that we've talked about how accuracy is very difficult to define at a qualitative level, quantitatively, what do we mean when we say the word accuracy? Well, in statistics, accuracy has a very specific definition, and it's broken down into four constituent parts: true positive, false positive, true negative, and false negative. And you can combine those in the equation shown here to get an overall accuracy. So you're taking your true positives, adding them to your true negatives, and then you're dividing that by the total number of examples that you have in your data set to get the relative accuracy. So what do these mean? A true positive is where you predict something is there, and in fact it is there. True positive. in this case, gritty, is in the image. False positive is where you predict something is there and it's incorrect. So in this case, predicting that a mascot is actually a reflection of a mascot, incorrect. A false negative is where you don't predict something is present when it is, or you predict something won't happen and it does. So in this case, we completely miss gritty up there at the top. And a true negative, probably the most problematic of the four categories, is when you don't predict that anything is there, and in fact, you're right, nothing is there. So if we go back to our equation for accuracy and look at what it means, we're combining these various categories into one summary metric. The trouble with accuracy is that for supervised machine learning projects, especially image recognition projects, classification projects generally, accuracy is a terrible measure of accuracy. I'll show you why. So, by the way, I don't know if the accuracy paradox is like a real thing or if it's just some grad student that put together a Wikipedia page that I found, but I very much believe in it. So one example would be finding construction equipment along a right-of-way. Imagine you're an oil and gas or pipeline monitoring company, and you're flying a plane along this very long horizontal piece of infrastructure looking for people, maybe without permission, digging along this pipeline. You're trying to catch them before they break ground and potentially cause an environmental hazard or even a human hazard. The trick is that most pipeline, at least in the United States, probably globally, looks like this. Empty, massive stretches of very narrow right-of-way. And so construction equipment is not parked along most of a pipeline's right-of-way. It's very rare that you would find that. Just to make the numbers easy, let's imagine while you were flying your plane, you took 10,000 images of pipeline. And in reality, only 100 of those, so 1%, contained some sort of vehicle at all. If we plug that into our accuracy equation, if we imagine there's a model that you run on that data and it has 100 true positives, so it caught every single example of vehicle, but it also has 200 false positives, so it's a little bit too sensitive. It predicts almost ghosts, where it thinks it's seeing a vehicle, but it's just seeing something maybe similar to the shape of a vehicle. That's a super useful model. And if we look at the actual accuracy score, we see it's a 0.98. The reason it's so useful is that if you think about practically what it means, you can trust this model to reduce a data set of 10,000 images, which would take forever for a human to look through, to just 300 high potential images that then a human could look through. And sure, you're going to have 2 bits of noise for every 1 true positive, but that still reduces the data set 97% from the raw data. So very useful model, 98% accurate. And let's say you, just to try it out, train another model, and that model goes horribly wrong. You write some piece of code incorrectly, and no matter what you show it, it says there are no vehicles in this imagery. It can be an image just chock full of construction equipment. And it will look at it and say, I don't see anything. I don't know what you're talking about. Essentially a completely useless model. If we plug in the values for that model, it has 0 true positives because it never catches any construction equipment, but it has 0 false positives because it never predicts that construction equipment are present no matter what. And when we look at what the result is when we run the accuracy measure for that, we find that it's 99% accurate. So it's more accurate than the extremely useful model. How is that possible? Well, it's possible because of a problem called class imbalance. And this is a very common example of, in statistics, what's called an irregular distribution. Work on this stretches back many decades. One of the most famous studies on class imbalance are really on irregular distributions and the deceptiveness of summary statistics is called Combs Quartet, done in the 70s. And that showed 4 separate, very different data sets with matching summary statistics to a pretty high degree of precision, showing that you really need to plot your data to understand it. You can't just rely on summary statistics. A more recent example is called the Data Source Dozen, put together by the Autodesk research team. I really love this. 12 very different looking data sets, all identical in their summary statistics to a pretty high degree of precision. So that's what's happening when you have 10,000 false negatives. It's just completely throwing off the distribution of the data and throwing off the results that you get. So then if we don't use accuracy to measure these models, what do we use? Well, two common basic building blocks that are very useful are precision and recall. And you can think of these as tools for understanding two different pieces of performance related to how the model is functioning. Precision, you can think of as, of all of the true positives that are predicted, what percent are correct? And so you're taking the true positives and dividing them by the true positives plus the false positives. So recall, on the other hand, is of all of the true positives in the data set, what percent did you actually catch? And so in that earlier example I gave, the model that was useful had a perfect recall, had a 100% recall, because there were 100 true positives and it caught 100 of them. But it had a fairly low precision, 2 false positives for every true positive. So it's a trade-off between precision and recall. And actually, if you plot them on a chart, what you find is that they're inversely related. And that's called the precision and recall curve. You can threshold your model at different areas along that curve to either preference precision or preference recall. F1 score then is a useful method for combining these into one summary statistic, because ultimately, if you think about the role of accuracy metrics, what you're using them for is not to tell you absolutely what the accuracy of a model is. It's to tell you relatively how it performs when compared with other models. So you're trying to figure out if, as you train iteratively, you're getting better or you're getting worse. So it's really useful to have one summary statistic to help you benchmark that process. That's the role of accuracy metrics. I'm not going to go into what F1 score is. Suffice to say, that weight, that number 2 on the left side of the equation, you can change that constant, and that changes how strongly you weight the precision part versus the recall part, which can be really helpful. So the reason F1 score is so useful is that it basically penalizes when you have a really weak precision or recall. So it's trying to incentivize balanced models that are more practical. So if we were to just take an average of those two measures, we're still dealing with this class imbalance problem. And you would see in these 3 examples, one has a 0.02 precision. It's basically useless. It just always predicts true positives constantly. And yeah, sure, it catches every true positive. It's got 100% recall, but it's just producing gibberish. And yet it's got the highest average between precision and recall. So we can't use just an average of the 2 scores. We have to use this weighted average, F1 score, and that gives us a much friendlier rating when we compare these various models to each other. And in this case, the evenly weighted balanced model comes out on top. So then the next logical question is, all right, what's a good F1 score if we're using F1 score as our measure? And I like to illustrate this with an analogy. So let's say you are having someone shoot at an apple on your head. You can choose between an archer that is 99% precise, but chickens out some of the time, only shoots 60% of the time, and another that is 60% precise. So those arrows are flying around all over the place, but they're going to take that shot every single time. Which would you prefer? Well, obviously, you would prefer the more precise archer, but in fact, they have the exact same F1 score. So again, reducing these things to a single variable without looking at the constituent parts based on the goals of your project is not very useful. Doesn't tell you much about whether or not you're going to be able to make use of this model in any sort of practical sense. F1 score is just one common metric, but there are many others. In the geospatial world, often you'll see intersection over union, sometimes called the Jacquard index after its inventor. And it's basically just the proportion of a prediction that overlaps with the ground truth. Really useful, actually, for measuring things like land use land cover, or any sort of semantic segmentation, pixel-based prediction, where you're trying to figure out how accurate a cartographic feature is compared to a ground truth. Another common tool is called average precision. You can calculate that by interpolating it in a series of discrete points, or you can use area under the curve to get a much more precise measure of it, which is what almost everyone does. I'm not going to go into a ton of detail about what area under the curve actually is, or what average precision actually is, but that itself becomes a further building block to more complex metrics like mean average precision, which is the average of the average precisions for each class in a data set or that a model is predicting on. This is actually super common in academic literature. Suffice to say, you can get pretty fancy with these measures, and actually it's worthwhile getting relatively complicated with the measures as long as you understand what they're telling you. And that's the trick, is that keeping track of what they're actually telling you is very difficult and something that you don't want to lose the thread on. But my actual favorite metric that I've ever seen used is no particular metric. It's a custom metric that was purpose-built to align the incentives of the model with the incentives of the problem that was trying to be solved. So a great example of this is the SpaceNet competitions, data science competitions put on by a group called CosmicWorks. They're a research lab from a federally owned venture capital firm, InQtel. And they put out research to help the geospatial analysis industry get better at extracting features that are important to federal agencies like roads and buildings, foundational GeoInt features. So they sat down and thought, well, if we're going to incentivize people to extract road networks out of digital globe imagery, high resolution satellite imagery, we have to think about why do we care about that data? Well, we care about it because we want to be able to efficiently route people in undermapped areas, or route resources to the right places in undermapped areas. That means we need a road network. We don't care about the actual road pixels. We care about the network that's represented by those pixels that allows us to then use them as a tool for logistics. So they looked at using F1 score for the competition that they were running, and they found that F1 score, you could have a fully connected road network that was sort of sloppy around the edges, and it would have a worse F1 score than a road network that was very precisely drawn but had a bunch of gaps in it. The trouble with having gaps in a road network is that you can't then use it for logistics. It thinks that's a dead end when in fact it's connected. So they should look for custom metric that would rank that second example over the third. And they came up with a metric called APLS. It's pretty complicated, but it snaps the results to a grid and then randomly traverses that grid to find how efficiently it can get from one point to another, and then ranks the road networks on completeness, essentially, and traversability, which is what you want to use it for, which I think is brilliant. The downside of that is that, the winning entrant had an APLS of something like 0.25 or 0.31 or something. So imagine explaining that to a client. Like, what does that mean? What does that measure mean? It's not very intuitive, but it's extremely useful for comparing models to each other. And again, that's the point of accuracy metrics. So accuracy metrics are really just one type of incentive when you're thinking about using machine learning and working with someone on a machine learning model. You have to be super careful about what those incentives really are. And, it's a common wisdom that you are what you measure, so you got to be careful what you measure. One example from past experience was a data science competition put on by Planet Labs, and really great competition trying to characterize change in the Amazon forest using planet imagery. What they did was they broke their images up into these small chips and then classified those chips according to what was contained in them. So you can see things like agriculture or water or road. They choose an F2 score as opposed to an F1 score, which I mentioned earlier, which means a recall is double weighted. And that makes a lot of sense because really what they are trying to figure out is is there illegal mining going on or is there deforestation happening? And we don't want to miss it if it is happening. So we prefer models that catch it as opposed to missing it. And this is very common. When you're looking for a needle in a haystack, preferring recall to precision is a very common pattern. But they decided to score it at a chip level. So there's thousands or tens of thousands of chips, and each one, the predictions on each are weighted equally. But that means that the rare classes constitute a much smaller percentage of overall chips than the very common classes. If we go back, things like clear, primary, meaning it's forest. There's nothing there but forest. Not that useful to detect that because we know that the majority of the Amazon is just covered in forest. And so, unfortunately, that resulted in models that didn't really do well at finding deforestation or illegal mining, that did really well at predicting clear rainforest images because that was the majority of the data set, and that's how that wound up getting weighted. The other thing that they didn't do is they didn't provide constraints on how this would be deployed or how many resources you could put toward it. And so one of the questions you have to ask yourself, apart from accuracy, is if you're comparing two models, one is extremely accurate but very resource intensive, and one is pretty accurate but very cheap to run, you have to factor that in. The winning entrant in this case had a very clever, really non-machine learning based haze removal pre-processing step that they ran, and that's what put them over the edge. So data preparation, not even like a new machine learning technique or something, just plain old data preparation helped them win. And their implementation, their winning model, had something like 11 or 12 separately trained models that would each independently make a prediction, and then another model would ensemble those results, meaning it would take the votes that were cast by each of these separate models, weight them based on what it knew they were good and bad at, and then make a final judgment as to how to predict. Trouble with that is, how long would it take to actually run that in production? How many GPUs would it take to even run that? I'll talk in a sec about what that would actually take. And for what type of gain and accuracy. For some context, the difference between the first place entrant and the 100th place entrant was just 0.004. So just barely improving on the 100th place distant entrant. It starts to get a little bit more downhill from that once you get to 500th place, but it's still not a huge change. We submitted into this competition. We came in 23rd place. We were 0.002 behind the winning entrant. That put us 23 places back. So you can see just how asymptotic this process is. And our best submission was 15 ensembled models. Again, totally impractical. It just did 0.01 better than our best single model did, which was very practical and very fast to run. So again, there's some practical considerations to this. If you think about it, there's over 1 billion acres of Amazon forest. 24,000 acres are contained in each planet scene, which means it takes 55,000 scenes to cover the entire Amazon. 222 chips in each one of those scenes means there's 12 million chips over the entire Amazon. If one model takes about 2 seconds to make a prediction on each chip, then it would take 9 months and 2 weeks of processing time to run that model over the entire Amazon. That's just if you have one efficient model. If you have 15 models, that takes 15 times longer to predict, so it's 30 seconds per chip. It's going to take you almost 12 years of compute time to run that over the entire Amazon. That's what I'm talking about in terms of inefficient or impractical solutions that are technically accurate. If we think about that in parallelized terms, because you can often parallelize this process over many computers, we're talking about the difference between 1,000 CPU cores running for 10 hours and 1,000 CPU cores running in parallel for 4 days. Very big difference. And this has been a problem since the very beginning of trying to incentivize machine learning for practical use cases. The Netflix prize was probably the most popular $1 million prize. This is back in 2009. And when they evaluated the results, they found that some of them worked in theory, but then the practical gains in efficiency, in accuracy, didn't overcome the impracticality of running it in production. We're talking about something running on 100,000 nodes that needed to run on 4 billion in production. That was back in 2009. Who knows what it is today? But here they are, handing out $1 million check for a model that they never used and couldn't even repurpose or take ideas from and implement in other ways. So that was a very expensive lesson. I also want to talk a little bit about fragile accuracy. So models are accurate insofar as they're measured against some ground truth, but that ground truth is a biased subset of all the data that could be shown to that model. And so you need to think about what could break the model in production. If it's trained on 5 centimeter imagery, that means it's not going to be accurate at all on 30 centimeter imagery. If it's trained over New York City, that means it's not going to work very well over Jakarta, most likely. If it's shown adversarial examples, is that going to completely confuse it? And that's going to be a weakness of the model that you have to worry about. There's a famous example of a sort of adversarial sticker that could be placed on the table to confuse a common object detection model and completely throw it off. And again, these aren't very intuitive looking adversarial examples, but it's very much a problem that you have to deal with in reality. These edge cases that you never would have thought about. Even just a simple noise filter that's invisible to the naked eye can be enough to throw off really sophisticated models. And my favorite example, juggalos with face paint on, defeating facial recognition algorithms because it can't tell where their chin is. So it's got no waypoint for figuring out the shape of their face. Here's an example of what that looks like. You can see the juggalo's chin is in the wrong place. So I just want to conclude with some practical advice that's hopefully helpful. Single evaluation metrics, they are not, like I mentioned, not descriptions of accuracy in any absolute sense. They're just a guidepost for telling you whether you're improving or getting worse. The only way to understand accuracy in any true sense is by looking at results qualitatively. So in Combs Quartet, it's looking at results plotted in a chart. In a lot of our work where we're doing computer vision, it's actually looking at the predictions on a map and seeing what they look like. Lastly, all models have trade-offs built into them. So if you're working with someone who's trained a model and they can't describe to you the strengths and weaknesses of that model, it means they don't understand it. And really what you're looking for is someone that advises you on which strengths to invest in and which weaknesses are okay and can be overcome. So with that, I hope you found that useful. For this conference, there's an opportunity to ask questions. I'm available in the chat, so ask away, and we'll make some extra time here for you to get all of your questions answered. Thank you very much.